In order to get the large-scale structure of the universe we see today, cosmologists have proposed the idea of inflation, that the universe expanded an enormous amount in the earliest moments. But if inflation really happened, then it has even stranger implications for the nature of the universe and the search for multiverses. We've covered this topic of inflation a couple of times in the past, but I'll give you the short version one more time. The Big Bang exquisitely explains the expansion of the universe that we see today. When we look out as far as we can to the edge of the observable universe, we see the afterglow of the Big Bang, the cosmic microwave background radiation. This light was released the moment the universe had cooled down a little and has been traveling for almost 13.8 billion years to reach us. Thanks to the expansion of the universe, it's been redshifted just a few degrees above absolute zero. When astronomers measure the temperature of this background, it's incredibly consistent with only tiny fluctuations, measurable with the most sensitive of instruments. This means that the entire universe that we can see had time to transfer temperature to each other before it expanded. But the original Big Bang theory suggested the expansion of the universe didn't give the material time to even out its temperature. In order to explain this, cosmologists developed the concept of inflation. There was a period in the earliest universe when the energy in matter was bound up in the fabric of space itself. The universe expanded so quickly that a region the size of a subatomic particle would have been stretched to the size of the visible universe in a fraction of a second. Inflation also answered other challenges that the original Big Bang couldn't explain, such as the flatness of the universe and the total lack of monopoles. Like I said, we've done a whole video about inflation. But inflation has introduced its own set of strange ideas, including the concept of eternal inflation. That inflation didn't end for the entire universe like it did in our local area. There are regions undergoing inflation all over the place, creating multiple universes within our universe, a multiverse. I'll be honest though, the concept of eternal inflation is beyond my comprehension. And so in times like this, I like to bring in a ringer. And today, I'm glad to bring you Dr. Ethan Siegel, an astrophysicist and science writer. His most recent book is Treknology, all about the science of Star Trek. Ethan tackles some of the most complex topics out there in an understandable way, and I could really use his help. Ethan, welcome to the Guide to Space.
Hi there, Fraser. It's my pleasure to be here, and I'm more than happy to tell you all about eternal inflation and why it lasts forever.
Last forever, it's going on, I don't even know where to start. All right, so can you sort of explain or add anything to the way I described inflation to kind of set the stage for how we're going to move into this idea of eternal inflation?
Sure, you did a great job. That's something that people don't realize when they hear the Big Bang. When people hear the Big Bang, they think, oh, that's the origin of everything, that's where the whole universe came from, and that's the birth of space and time. And as far as we're concerned, the answers to that are yes, yes, and not quite. The reason is, if you imagine the universe today, you see it expanding, you see it cooling, you see galaxies moving farther and farther apart from one another, and you say to yourself, oh, right, well, if things are expanding now and cooling now, right, the redshift you talk about, because as space expands, as the fabric of space stretches, you say, oh, right, you have this wavelength of light, and that defines its energy, so as space stretches, the wavelength gets longer, and that means the universe gets cooler. So if instead you look back in the past and say, what were things like in the distant past? You'll say, oh, right, well, that means that the universe was smaller, and space was smaller, and things were closer together. So rather than being larger and getting cooler, that means in the past it was hotter, it was denser, things were closer together, and because it's had less time for things to clump together, the universe was also more uniform. So you extrapolate back and you say, well, if things were hotter and hotter and hotter and more uniform, then I should be able to go back to a time where there were no stars and no galaxies. And we think we've seen that time, and we think that the James Webb Space Telescope is going to reveal those first stars and galaxies. And you go back even more and you say, well, at some point it must have been so hot and these wavelengths of light must have been so short that you couldn't have even formed neutral atoms at that time. And absolutely, that's correct. You should say there was a time where the universe was just full of an ionized plasma because all of the radiation in it was too powerful, that as soon as you formed a neutral atom, an incoming photon would strike that atom, knock the electron off, and you'd have a plasma again. When you talked about the cosmic microwave background, that refers to when atoms finally became neutral, that scattering didn't occur anymore. And that's the leftover glow we see from the Big Bang, which happened when the universe was 380,000 years old. You go back further, and it becomes so hot that you can't even have atomic nuclei, that they get blasted apart. So we can do the calculations for the light elements, for the abundance of the light elements, for how nuclear fusion happens in these first few seconds and minutes of the universe. And that's something that we make predictions for, that we have observations, and we learn about the universe. But if you want to go all the way back to arbitrarily high densities, to arbitrarily high temperatures, you run into a problem. You start saying, well, if that's what I got, then what I should see, for example, in this pattern of fluctuations in the microwave background, is that different regions should have different temperatures of a certain magnitude. There should be big massive temperature fluctuations that we don't see. We don't see like 1 part in 1 or 1 part in 10 or 1 part in 100 fluctuations. We see like 1 part in 30,000. Which tells us, no, there's a lower energy scale there. There's a cutoff. We would expect that if you look 13.8 billion light years in one direction and 13.8 billion light years in the opposite direction, there's no way for these two regions to have exchanged information, to have exchanged photons, to have come to thermal equilibrium. And yet, completely opposite regions of the sky started off with the same properties somehow. You also talked about spatial curvature, and we measure the spatial curvature of the universe to be 0, for it to be absolutely flat, even though we know spatial curvature increases as time goes on. So that means when the universe was 10 to the minus some really large number of seconds old, it would have had to have a curvature that was super minuscule, like 10 to the minus 100, in order to give roughly 0 curvature that we see now. So all of these things are motivations to say, either to get the Big Bang, we had to start with these incredibly finely tuned initial conditions. Or you can appeal to physics and say, what type of dynamics could have occurred to set this up? This is the beginnings of where you get any scientific theory from. You have a theory, the Big Bang, that works really well in a certain regime. But when you go all the way back to the very beginning, you start asking questions that you don't have a good answer to. You either have to say, well, it was just like this, and that's the story. Or you can say, well, it started off with these sets of conditions. It was flat. It was the same temperature everywhere. We don't have these high energy leftover relics that all the extensions predict. Either we start with those conditions, and those are the conditions the universe is born with, or something happened to set the universe up like this. And if that's the case, if something happened to set the universe up like this, what are the other things that this theory would predict? And how can we go out and test them? So that's what inflation is.
Right, and so that sort of sets the stage for what inflation is. It's this expansion that I mentioned that you were talking about. But in my mind, I imagine it being this thing that happens across the entire universe, this stretching that happens at all places at once, and then that phase of it is over. So how does this lead to the idea of eternal inflation?
Okay, so that's a great explanation, right? You have this space and it's stretching exponentially. And just so everyone knows what exponentially means, imagine I've got a little cube that's 1 centimeter on a side, and I let it expand for 1 time step. So I take a time step, and now it's 2 on a side and 2 on a side and 2 on a side. So it's 2 by 2 by 2. And then I take another time step. And so now each of these has expanded again. So it's 4 by 4 by 4. And then I take another time step, and each of those again doubles. So it's 8 by 8 by 8. You can see with inflation that if you just take a small number of time steps, like 64 time steps or so, all of a sudden you get something that's like 10 to the 30 times as large as you started with. which is to say that if inflation goes on for just 10 to the minus 33 seconds, then you can go from something the size of the Planck scale, the smallest conceivable scale that makes physical sense, to the size of the observable universe today in just 10 to the minus 33 seconds. So that's how rapidly space expands. That's what it means that it's expanding exponentially. So then you say, okay, how does this happen? And you say, well, I can imagine that it's some quantum field that, when you're up at the top of a hill, right, you get inflation going. And then you roll down the hill and inflation comes to an end. And you say, okay, that's great. And you told me this picture you have, that inflation starts out here, you roll down the hill, and it comes to an end, and it does that everywhere. And that's fine if you're a ball rolling down the hill. But we know that inflation, like everything else in the universe, should be a quantum field. It's not a ball rolling down the hill, it's a quantum field running down a quantum potential. So now let me ask you something about quantum mechanics. If I give you an electron and I say, hey, hang on to this electron, and you do, and you hold the electron in your hand as though that were something you could do to electrons. And then I say, hey, just take a chill pill. Don't look at that electron for a while. Chill out, let that electron sit in your hand, and come back after a couple of seconds. Now, where's that electron? Is it in the same spot you left it? And you can go and look. And there's a probability that the electron will be in the same spot you left it. But one of the properties of quantum wave functions is they spread out over time. Right? This is something that's just inherent to the quantum nature of every particle and wave in the universe is it has this inherent uncertainty to it, and it has this inherent quantum spreading to its wave function that happens with time. So if you've got your inflationary, potential, if you've got the field at the top of a hill, right? The field's at the top of the potential and it starts to roll. So it starts to roll down the hill. You can say, well, hang on. As it starts to roll, instead of having this 1 by 1 by 1 box, I've got this, let's say this 8 by 8 by 8 box. I've got 8 times 8 times 8. That's a lot. That's 512 independent regions that were the size of that original region. And then you say, okay, well, it started to roll down the hill. That's on average. So on average, it started to roll down the hill. But because of this quantum nature of things, the field spreads out. What happens then? The field spreads out. So in some places, you've rolled farther down the hill and you're closer to inflation coming to an end. In some places, you're right where you expect to be, where inflation's rolled down the hill, the field's rolled down the hill, and inflation's coming to an end like you expect. But in other places, inflation has actually caused this spreading so much that you are closer to being back up the hill than you were initially. In other words, you don't always roll down the hill, even if it's just a small percentage of the time where you run up the hill, where you run against where you expect it to be, because this quantum spreading is faster and bigger than the rolling down the hill. Well, space grows so fast from one thing to 512 things in such a small time that now you see, oh no, I have more regions that are inflating even more than they were when I started. And so, yes, you're going to have regions where inflation rolls down that hill, where it comes to an end, and where it comes to an end, that's where that energy inherent to space gets converted into matter, antimatter, and radiation, and you get that hot Big Bang, and you get the birth of our universe with all those properties that we talked about, where it's been stretched flat, where it's the same temperature in all directions because things were connected during inflation, and where you don't have monopoles or other high energy relics because you never got up to that high temperature that you thought you would get if you extrapolated arbitrarily. There's a maximum limit to the temperature we reach, and we discovered that with the WMAP and Planck satellites, that's somewhere around a factor of 1,000 or more below the Planck energy. So, okay, with inflation, you can reproduce those successes of the Big Bang. You can make additional predictions about the fluctuations in the universe, about superhorizon fluctuations, about what types of structure you're going to get. But you can also do this additional thing where you say, well, where does inflation end? How likely are we to have inflation end at any particular time? And you can say, well, look, as we move forward in time, even if inflation comes to an end with every time step in half or more than half of the regions, there are still an infinite number and an increasingly infinite number of regions as time goes on where inflation continues for an eternity. And that's where the idea of eternal inflation comes from. That as this quantum field rolls down the hill, it has a probability of spreading out. And in some of those regions where it spreads out enough, you never roll down that hill. You always stay at the top of the hill, which means you're always inflating.
And so if we looked across the universe, if we could somehow kind of move into a God mode and actually look around and observe, we've got our current observable universes, which is only some fraction of what is the possible actual universe and possibly infinite. But if we could see these other regions of inflation, what would we see?
Okay, so I'm going to ask you to visualize it as though you were some higher dimensional creature, that you could see all the 4 dimensions of our space and time, and you can see what's going on in them from an outside view. Inside, you would see what we call our observable universe. This is the stuff we can see, from the moment of the Big Bang, the light that's reaching us right now in all directions. It would be this spherical region centered on us, and only centered on us because that's where we happen to be. If we were anywhere else, it would be centered on wherever we were. And you would see that that's a part of our region where inflation ended. It's getting bigger as time goes on, but we can't see all of it. Now, if you look beyond that, beyond the part that's observable to us, you would also start to see, oh wow, we're getting a big spherical region that is where inflation ended. And it may not be spherical, it may be asymmetrical. We just assume it's spherical. But you get this big region where inflation ended, and that's expanding outward at the speed of light and also with the expansion of space. And anywhere within that region, if you put down an observer and say, hey, you've been here since the Big Bang, what do you see? You could draw a sphere about 46 billion light years in radius around them, the same as you can for us. That's how far you can see in the expanding universe. Except if you're very close to the boundary, you would get there and then you would see a mysterious end. You would see just like a cutoff in the structure of your universe, in the cosmic microwave background, and there would just be empty space beyond that. So then, if you say, well, what's going on in that empty space? Well, outside of the region where you had your hot Big Bang, that's inflating space. That you would have this space where inflation continues. And every so often, you can say, well, if I look throughout this inflating space, what else am I seeing? And the answer is, well, I would see a bunch of different pockets in the universe that looked like our part where inflation ended, except it may have ended at different times. So the universe in some places, right, other universes within this multiverse, within this eternally expanding space, they may have not ended 13.8 billion years ago, and said that's when you have the Big Bang and that's when you get your little pocket universe. Instead, you could have something that ended more recently. You could have something that ended long before us. You could have universes older than ours is. And you can also have a universe where inflation is just ending right now and you're only having the start of that hot Big Bang. But what's very important to recognize about inflation is this super rapidness at which it causes space to expand ensures that if you envision the universe as, okay, we've got this little bubble that we formed within this, ocean of inflating space, and then we've got another little bubble, even though these bubbles are expanding at the speed of light, the space in between them, the space that's inflating, is expanding exponentially, and it always pushes these bubbles away. In other words, no matter where you are in the universe, your pocket universe should never ever collide with another pocket universe. The space in between them should always be expanding eternally. And even though you're always producing a countless number of these universes, they'll never interact with each other and we'll never be able to see them. All we can experience is our observable universe from within it.
So we can just never reach any of these other universes. We're stuck just doing the math and imagining them. That's sad.
Right, unless you turn on God mode, like you said. If you turn on the God mode, then you can see all the things. And this is an interesting thing because a lot of people argue, well, is the multiverse and is eternal inflation actually science then? And I would argue that it is, but you have to be very careful. The reason I would argue that it is you say, well, we've got this theory of cosmic inflation and the evidence for it is overwhelming, right? We've got some very good evidence for it. Cosmic inflation has been validated. It's very robust. We're very happy with it. Then you come to the next thing and you say, well, but we also understand that the universe and everything in it is quantum in nature. So you say, okay, we've got cosmic inflation. We've got the quantum nature of the universe. We put these two things together and what are the consequences we get out? And eternal inflation is one of them. This tells you no matter how long ago or how recently ago inflation began, once it begins, it should continue eternally into the future. This doesn't mean it continued eternally into the past. Inflation may have had a beginning. The universe may have had a beginning. Or it may have been eternal to the past. The problem is for us within our observable universe, because of how rapidly inflation causes an expansion, when we look to one end of the universe and when we look to the other end of the universe in two opposite directions and we say, okay, we're looking at the entire observable universe, how much of inflation do we have access to? Do we have information about that exists in something observable to us? The answer is, unfortunately, we only have access to about 10 to the minus 33 seconds, the final 10 to the minus 33 seconds of inflation. This is something that could have gone on for fractions of a second, or it could have gone on for many seconds, or years, or billions of years, or Googles of years, or forever. But we only have access to that tiny bit of information. So on one hand, it's incredible how much we can learn about the universe just from this tiny bit we can access. But it does make you wonder, because we have this tremendous extrapolation that we've done from it, is there some new physics somewhere? Or is there some physics that we've gotten wrong along the path that means that this conclusion is invalid? And as a scientist, it's very important to keep an open mind about it. We're doing the best science we can with all of the information we have. We validated every part of this theory that we can physically validate. And for the parts that we haven't validated yet, we're looking for ways to do that. But as we come forward, we hope to learn more and more things, but at some point you're going to hit a limit. You're going to hit a limit. There's a finite number of particles in the universe. There's a finite number of degrees of freedom they have. There's a finite number of bits of information encoded in it. And we, even with everything we have, the 10 to the 90 particles or so, and how they're correlated and interact with each other, that's finite. And so if you say, I want to know what happened before these last 10 to the minus 33 seconds of inflation, that information might not exist in a way that human beings or anything within our universe can ever gain access to.
Oh. Well, in a moment, Ethan and I are going to talk about his new book. But first, I'd like to thank Lucas Ungaro, Kane Doyle, Jackson Van Diesen, and the rest of our 812 patrons for their generous support. If you love what we're doing, you want to get in on the action, head over to patreon.com/universetoday. Ethan, well, thank you very much for blowing my mind with this sort of bittersweet ending. But tell me about your book. Congratulations.
Yeah. So thank you. I have a new book out. It's called Treknology. It's a book about Star Trek, the science of it in particular. It's about the science of Star Trek from tricorders to warp drive. And what we've done in this book is we've taken a look at 28 of the different technologies featured in Star Trek, from warp drive to transporters to tricorders to Geordi's visor to any of the military or civilian or communication advances you can think of, to the ship's technology, to even like Borg implants. You know, you take a look at these technologies and you want to ask yourself, well, Star Trek the original series was 51 years ago. Star Trek The Next Generation premiered 30 years ago. How many of these technologies have already become reality? You've got things like flip communicators and universal translator earpieces and touchscreen computers like pads or electronic clipboards and sliding doors, and you're like, that's yesterday's technology, and that's true. In the meantime, we've made tremendous advances towards some technologies you might not even realize are literally almost here. From a holodeck, we've got virtual reality with multi-sensory experiences, not just sights and sounds, but using infrasonic sensors. We've also got touch. You might say, well, what about things like synthahol? And believe it or not, we've actually got drugs and pharmacological compounds that have us well on our way to having a synthetic version of alcohol that will give you all of the positive effects without any of the negative effects, and in addition, that you can take an antidote pill for to sober yourself up almost instantaneously. We've got the ability, you remember Geordi had his visor and later he got ocular implants. Well, it turns out that they've developed a cortical implant they can put into your brain's visual cortex that can restore sight to up to 85% of blind people, including those that don't even have any optic nerves to go through.
Fantastic. Well, Ethan, we're going to put a link to the book in the show notes of this episode, and people can go and get a copy. You're bordering on spoilers, but it sounds absolutely terrific, and I can't wait to give it a read. All right, well, Ethan, thank you so much for joining us on the Guide to Space today. Really appreciate it. If people have questions, I'm going to encourage them to post them in the comments, and maybe you can show up and answer a couple of people's questions.
I'd love that. Thank you.
That sounds great. All right, well, I think this episode deserves a playlist, and this time you're going to get a series of really complex lectures and documentaries, but I think you can handle it. First up, a lecture from Leonard Susskind about eternal inflation, a short animated video about cosmic inflation, another from PBS Space Time about inflation, a lecture from Lawrence Krauss about inflation, and finally, a video from the Perimeter Institute about the search for a multiverse. And that starts right now. This light was released the moment the universe... Really? Oh.